Hello, my name is Peter Skiprine and welcome to this video about particle swarm optimization, a simple yet powerful and versatile optimization method for solving many types of problems. I'm a retired optimization engineer with a major energy company, and during my tenure I had the opportunity to learn and apply PSO in solving business problems. And it is this algorithm that I want to talk about with you today. I've geared the discussion toward the beginner who may or may not have experience with it before, but others may still enjoy the use case discussion later on, so stick around. The concept behind PSO is as outlined here. A swarm of particles traverse a solution space in search of the best location, learning from each other along their journey. Here's the agenda for the video. We're going to begin with a conceptual understanding of the PSO algorithm. Then we're going to do a deep dive in terms of the mathematics of how the particle motion works. What I think is the most interesting part of this is going to be exploring how PSO can solve 5 diverse use cases in the learning by example section. And we'll wrap it up with a checklist and see if PSO is going to be a good choice for solving your problem. And then finally, tips on implementation. So although the algorithm is called particle swarm optimization, we can think of it as flocking bird optimization as well. So the question is, what governs the flight path of a bird? Well, there's 3 components. We can think about the position of the lead bird. The other birds will follow. We can think about the bird's memories. As it is traversing a cornfield in search of food, it might have flown over what it considered at one time the best place to look for food. And then finally, the inertia component in terms of the direction it has been going is going to have an influence in the direction it will be going. And it is these 3 components of motion that are important to the algorithm. So we can think of PSO as an optimization algorithm that mimics the social behavior of flocking creatures in their collective movement. And it's attributed to these gentlemen here, James Kennedy and Russell Eberhardt. They produced a paper in 1995. I don't have the reference here, but it's easy to look up. And what they wanted to achieve was simulate social behavior using the stylized movement of swarming creatures as a metaphor. Kennedy is a social psychologist and Eberhardt an electrical engineer interested in evolutionary algorithms. Here's a flowchart of how the PSO algorithm works. We can think of this type of algorithm as guess, test, and repeat, but there is logic to the progression rather than random exploration. To begin, we need to initialize the swarm. That is to give each particle a starting location in the solution space. So if we stick with the metaphor of birds locating food in a cornfield, our solution space is going to have 2 components. There's going to be an X direction and there's going to be a Y direction in terms of the location of that bird. And so we need to give a starting point for each bird that we're going to have in our swarm. Now, typically that's going to be a random location, but it doesn't have to be. You can start this also with some sort of a structured grid or orientation. Then what we're going to do is assess the fitness of each particle. So given where that particle is or that bird is right now in that cornfield, how much food has it found? Is it a low food location, high food, no food, whatever? But we need to be able to compute that for each bird. Then we have to do some accounting. We have to keep track of the particle and the global best position. So for the particle, it is as this bird traverses through the cornfield, we're going to keep track of the location historically that it's found the best food source. And in case it moves to a new location that has a better food source, we're going to update that as the particle best. We're also going to keep track of all the birds, where was the best location so far. And so what we want to do is keep track of those things because it is going to be 2 components that are going to govern the future motion of the birds through the iterations. That's going to help us decide where the particle goes next. So each particle adjusts its velocity considering its historical personal best position and swarm's global best, along with the inertia. Remember that slide I showed you about those three components. This guides movement towards better solutions. Once we have the new velocity, we can then move these particles. So we're going to update the particle's position by adding the velocity vector. This iteratively drives the search process forward. Stopping conditions. We'll keep doing this until we've met some sort of a stopping condition, be it we've achieved maximum iterations, we have the objective satisfied, improvement becomes stagnant, and so forth. And finally, we're going to return the objective of the global best. Thinking about that flowchart I just showed you, this is what the pseudocode could look like for particle swarm. We're going to begin with initializing that swarm, but really, as you can see, the core of the algorithm is very simple. It's composed of two nested loops, the outer one being for each iteration and the inner one each particle. First thing we're going to do for each particle is assess the fitness, or we're going to see what is the score of an objective function that returns the fitness for that particle at its current location. We're going to determine if we need to update that particle best. Is this the best location that particular particle has seen so far? And keep track of if we need to update the global best as well. Once we've done this bookkeeping, then it's a matter of moving each particle in the swarm. So we compute the new velocity for that particle, and we're going to add that to its position to update and create the new position for the particle. And finally, determine if stopping conditions are met. To do that, we have a bunch of dedicated procedures, initializing the swarm, for example, that fitness function I talked about, and then updating velocity, updating position, and also stopping conditions. Let's get into the mechanics of moving a particle. So particles move from one iteration to the next, and the number of variables to solve for is the same as the dimension of the solution space. So using that bird cornfield metaphor, we have the X position, we have the Y position, and that's how we want to move the current position to the new position. The first motion equation is inertia, so that's just the same as the current velocity, how it got to the current location. We just add that vector outbound in the same orientation. Cognitive relates to the where is the best position related to the current position of that particular particle. And we're going to multiply that by two components here. We have a parameter called C1, and that's going to be weighting factors, usually between the values of 0 and 2. These are going to be defined ahead of time for the particle itself, and then keeping track of the global best. And then we also have these random numbers, R1 and R2. They are uniformly distributed random numbers between the values of 0 and 1. A third component here is called W, and why they didn't call it C3, I don't know. But anyways, W is an inertia weighting factor related to that current velocity. Usually the value is around 1. Okay, so the cognitive vector, that's this guy here, so that's going to be C1 times R1, best position minus the current position of X and Y. Then there's the social component, which is, the equation looks exactly the same, but instead of it being the best position for that particle, we're going to use the location of the current global best minus the current position. So the new velocity is going to be the vector math of these three things. So we got inertia, societal, cognitive, that becomes the new velocity. We add the new velocity to the current position, and that gives us the new particle location. Let's run through a numbers example how this works. So given that we have C1 set at 2.0, C2 1.0, random R1 0.4, random R2 0.5, and finally W at 0.9, we have our current location at 3.4, current velocity is 2, 1, and particle best and global best are shown here. So how is this working? All right, we have the motion equations. Remember, inertia is 2, 1. We plug in those numbers to our equations, and remember, we're optimizing in the x and y locations. So that's going to be the 2, 2 for the particle best, the 3, 4 for the current location, and that turns out to have a vector of negative 0.8 and negative 1.6. We do the same thing with societal. And you can see as we plug in the math, we plug in this, instead of it being the particle best, we're now plugging in the value of the global best. We do the calculations. We wind up with a weighting component of 2.5 in the x and 0 in the y. And finally, the new velocity is going to be the combination of those things with inertia. So the new position is going to be at 6.5 and 3.3. That's going to be there. And in the next iteration, the current position becomes the new position, and the inertia becomes the new velocity. We update if we found from where the new location is, we update if the global best and or the particle best need to change. Let's use this chart here to understand the influence of C1 and C2 on particle movement. When C1 is equal to 0, trajectory is totally global best dependent. We are exploration focused. Let's assume for now that the inertia is 0, so we are totally on this line here, moving towards global best exclusively. Conversely, if C2 is equal to 0, trajectory is totally dependent on personal best, and we are exploitation focused here. We can split the difference, for example, if C1 and C2 are the same. So then we're going to wind up with this vector here. And again, the weighting of, depending if we're a little bit more global best or a little bit more personal best focused with the values of C1 and C2, that's going to determine this swing here. The larger the value, the greater the tendency to overshoot and explore. So you can see then a value of 1, for example, that gets you here. And let's just assume for the sake of argument that random R1 and R2, we're going to set those to 0.5. If then the value is 2, we wind up right at the global best and so forth. So you can see then how the magnitude and the direction of movement is influenced by C1 and C2. An interesting concept that you could apply is that through the iterations is to vary the values of C1 and C2. This may offer an optimum strategy for exploring new areas at the outset and exploiting known promising regions later through manipulating the values of those coefficients. Let's explore the interaction of inertia, societal, and cognitive components on particle movement. If we were only inertia dependent, so C1 and C2 is equal to 0, we're going to dash towards the boundary. What's interesting here is because the weighting factor for inertia was set to 0.9, this movement decays over time. If it was 1, we would keep moving with the same distance, and eventually we'd wind up towards a boundary. But in this case, because it's less, we decay and will eventually stop. So really, that's not a good strategy for exploring the space. What if we were personal best dependent, or set C1 to 1.0 and C2 is going to be 0? Then we are all cognitive and trapped in inertia. So remember, we can still only move along that vector, and we're going to find along that movement a personal best location where we will eventually cause it to move back towards. But because there's no interaction of the components themselves, there's no societal interaction since C2 is set to 0, we still stay along that inertia direction. Now what happens if we are totally societal dependent with no personal best? So what's going on here is we have located a global best somewhere around here, it looks like, and our particles are just going to scream towards it. Occasionally you can see a little bend in the vector as we located a new global best, but there's no cognitive component here, so we just scream directly towards the so far found global best, with perhaps missing other locations in our potential solution space. And finally, which is actually the strategy that we want to use, we're going to employ values, non-zero values for both C1 and C2, in this case 1.0, where we have a good balance of exploitation with exploration. As you can see now, we've explored a lot more of the potential space, and it looks like we've located the true value around this location here. With an understanding now of how the algorithm works and how the particles move, let's get into 5 different use cases. So we'll continue on with the cornfield example. Then sticking in 2D space, however, now we're going to spot radio towers that maximizes the population covered by that network. Then moving on to function fitting. So this will be decline curve analysis to forecast the future production of oil field wells. Then move into time series. So how can we determine the burn profile to successfully land the LEM on the moon? And wrapping things up with nonlinear blending. Let's get into it. Birds in search of food in the cornfield. All right, our objective, find the best food location in the cornfield. The parameters, x and y coordinates, that turns into position and velocity vectors for each particle. So that would be x, y. Each particle location represents an instance of the solution. Understanding particle locations through iterations. So here we have our synthetic favorability index of food in the cornfield. We have a local optimum here. We have a global optimum here. As you can see, yellows are good, dark blues are bad, no food. And so the object is to find this location. Although we can immediately spot this because we know what the map is, the birds don't know this because except for the places they've already been, the favorability surface is hidden to them. Because of the stochastic nature of the algorithm, particle paths will vary run to run. Getting inconsistent results is an indication of the algorithm has not been sufficiently tuned. But be that as it may, let's walk through the iterations here and see what we discover. So in iteration 1, we randomly positioned the birds, we've calculated their fitness. This one here is very close to that local optimum. It's colored red. And so right now, the birds are going to swarm towards this guy here as the societal component. If we move on to iteration 5, on the way of doing that, as you can see, birds have already started to cluster here. Another bird, in the meantime, has found a better location here on the flank of this global optimum here. So as we continue on, iteration 14 now, the birds start to converge to that global best. And continuing on still further, this is now iteration 34. We've basically ended the algorithm with us located at the peak of that global best. So that was good news how the algorithm works. But you can see how the global best can shift through iteration. First the suboptimal or the local optimum on the flank, close to the top, and finally, as you know, looks like we're very, very close, if not right on the top of that global optimum. Let's understand the interrelationship of the population size with C1 and C2 configurations. So what I did was I ran the algorithms hundreds of times with different numbers of particles and different configuration for C2 and C1. Okay, let's see what it looks like with a small population of only 10. Now this is not going to be our map view of the cornfield. This is going to be the objective returned, or the global best, at different societal and cognitive weighting. So this is going to be C2 and C1. And you can see we have a lot of kind of greens, light yellows, somewhere in here. We knew that the objective was actually up in 6. We're not finding that bright yellow. This is a small population size, but we would think that the area in here performs generally worse than the area up in here. All right, let's move on to 20. Same sort of deal here. We are seeing some higher yellows here, but it's definitely not consistent. So this is, again, these values here are the averaging of many different runs, and then finding what that average is. So some of those runs we might get a very good fit, but not on all of them. Let's keep bumping up that population. We start to see more yellows here, not consistent though, but definitely more than in 10 or 20, 40, same thing, but more of it now. We continue on with 50. Yep, we're now getting lots of yellow up in this space here when societal and cognitive are above 1. So this would seem to be a good configuration with 50. And finally, if we flood the field with 100 birds, we see that regardless of what the C1 or C2 is, we're going to have a good match. So this is akin to sort of a random brute force exploration. Of course, the more birds or the more particles we have, the longer the algorithm is going to run. So it's really depending for your particular problem, what is your budget in terms of time, and how close do you really have to be to finding that true optimum, or are you willing with something, are you satisfied with something close to the best? Let's make the cornfield example a little bit more challenging, and rather than one local optimum and one global, let's think about some stacks of corn out in this field. So we have many local optimum here, you could see, and then a global one here that's bright yellow. How would the algorithm perform in this sort of a situation? So if we run the algorithm with 20 birds and 20% regeneration, so that means as we proceed through the iterations, the 20% worst performing birds, we're going to respawn them, as it were, and put them randomly back in the field and see if we can improve the freshness of our exploration and continue on. What we're plotting here are all the global bests found through the iterations. So that global best has shifted between, we first wound up here on this stack down at the bottom, and then we migrated, it looks like we went to this guy here. And finally, we wound up on the flank and then at the top of what is indeed our global optimum. So I think this is a pretty good example of how the search space, or how the algorithm can search through local optimum to get to a global one. Moving on to our next use case, let's cite radio towers. Instead of finding one best location, let's find several. For this example, we're going to use a city in the Netherlands called The Hague, or Den Haag. And I went online and searched a bunch of sources and sort of massaged a map, and I came up with this population density map. So you can see here, we're centered on the central train station here at zero grid. These are KMs away from that distance. The central government district downtown is located here off to the west. The beach town of Scheveningen is up here. North Sea is here. Not many people living there. We have a little less population here off to the east, as well as the southeast. So that's going to be the input for our tower siting use case. Our PSO setup is as follows. The goal, optimize placement of towers to cover maximum number of city inhabitants. Fitness function, sum of population covered under union of tower coverage areas. And so what this means is we're not going to get double credit when those coverage areas overlap. Position vector is tower location, so x1 and y1 of tower 1, x2, y2, and so forth. The model parameters, number of towers, I did two different situations, one with only 4 towers with a radius of cover 2.5, one at 9 with 2.0. Key algorithm parameters, we got C1, 2, C2 is equal to 1, so we're exploration biased. Number of particles, 20 for 4 towers, 40 for 9. Regen, worst 20 performing particles to preserve swarm diversity. And we had stop-time criteria of maximum iteration 500, stagnation set at 50. All right, let's take a look at that 4-tower layout random start. And if we initialize the swarm, we wind up with this situation here. Now, it's important to keep in mind that each tower does not represent a particle, but rather we have 20 particles, and that of those 20, this configuration here produced the global best result so far. So that's what we're seeing with these tower locations. But be that as it may, as you would expect, we're not doing that great. We have a lot of overlap. We have missing space not being covered here for a total coverage of 300,000 people. Moving on, after iteration 5, we've already improved it to 26,000 people. And we've reduced the overlap, which means we've also started to improve the coverage, moved a little bit away from also what's going on with the overlap over the ocean. And now we're at iteration 47, 343,000 people. Again, we're starting to spread out those towers, reduce the overlap, continuing on to iteration 235, 365,000 people now. And what I found interesting here is that you can start to see this diamond pattern emerge that's even more prevalent when we wound up at our final iteration at 471 after we reached stagnation and we covered 370,000 people. The diamond configuration is indicative of hexagonal close pack strategy for spheres of constant size or circles of constant size in a 2D space. So although the algorithm itself has no idea what hexagonal close pack is, it sort of mimicked that in how it came to find the best configuration for the tower locations. This graph here overlays the heat density map with the location of the towers through the iterations. So we started out with the dark blues here, and eventually we migrated on. And what I found to be fascinating is that as we went through here, we sort of started down here, and then we migrated here, started here, migrated to here. So it looks to me like it's going in a counterclockwise direction, and it's an example of how the location of one tower impacts the others and vice versa, how the algorithm finds the optimum location. I thought that was pretty cool. All right, let's do the same thing with 4-tower, but a grid start. So we have our start here with the grid, and we wound up with a already improvement of 351,000 folks. Let's see if we can do better than the original random approach. And at iteration 5, we increased that by 8,000 folks to 359. We moved away from the North Sea. Iteration 15, starting to get that diamond appearance once again, which I think is neat. And that continues to be manifested as we move on to iteration 77. We're now at 368,000 people covered. And finally, stagnation occurred at iteration 154 for 369,000. So it's interesting that with the grid start, we didn't have to work as hard, but we really got the same answer, or very close to the original answer for the random start. And this is something for you to consider when you do the implementation of PSO. What sort of starting conditions do you want? Do you want some sort of a randomized start, or is there some structure that you can use for your problem to have the algorithm work as efficiently as possible? Here's that location chart of the individual locations of the towers through the iterations. And in this case, you can see where we started. There wasn't as much movement with the grid start. Again, maybe an indication of the algorithm's not working as hard, but it really came up with the same answer as the random start. Let's now take a look at a 9-tower layout. So the algorithm is going to work even more now, trying to spot those 9. We used a random start, so we came up with, here's our 9. You can see lots of overlap for 9, I believe. What was it, 40 particles? So this was the best of 40 of a layout for the towers, but still lots of overlap, so lots of room for improvement with a coverage of 353,000 people. Moving on now to iteration 5, we've increased that to 382,000. Still lots of overlap. We have moved away from the sea a little bit. The amount of space that isn't covered has decreased. We're moving on again, and this I thought was kind of neat, the way now we get this geometry showing up of the overlap that minimizes the uncovered space. Continuing on, we see more of that, and after iteration 225, we now have 441,000 people. And finally, when the algorithm stopped at 450 iteration, we now have covered 447,000 folks. And again, you can see the diamonds throughout here that that I think is a kind of a fascinating artifact of the algorithm migrating towards a hexagonal closed pack type of solution. Moving on to our third use case, this is going to be automating decline curve analysis or fitting a function to time series data. So I've been to fields that look like this, and there are hundreds of wells in some of these old mature fields, and a production engineer may be responsible for many of them, responsible for 100+ wells. And one of their functions is to project or forecast out what that production trend is going to look like for various reasons. So it's like so many wells, so little time, and any chance to automate some of that work is going to be greatly appreciated. So with decline curve analysis, we are fitting what is known as a hyperbolic function to our observation of data so that we can minimize the error between the function and the data and then project out the function. So what we're trying to do is find the coefficients of the hyperbolic function that minimize that error. Now, for DCA uses, there are several. First is production forecasting, as I mentioned before. That ties into reserves management. We can also use it to establish a trend and then determine if that well is starting to slip off of that trend. So we can spot the decliners that may need maintenance scheduling. And then use it to forecast the capital allocation necessary to maintain the field through the process of business planning. Benefits of automation are several. First of all, saves the engineer's time. Consistent and repeatable results, eliminates the bias and human errors much faster than the human doing it, and may be performed at regular intervals. The computer never sleeps. Here is the PSO setup. The goal is to minimize the root mean squared error of observation versus fitted function. The fitness function itself is the hyperbolic, and these are the components of that. T is equal to time, QT is the rate at time t, QI is the initial rate, D is the decline, and B is the power of decline. So our position vector, or what we're trying to solve for, are these three things. It's going to be QI, D, and B. Some PSO parameters we're going to set up are the C1 and C2 values set at 1.5, number of particles 25, the W factor for the inertia is 0.8, and extinguish percent of 30% to preserve diversity. Stopping criteria, either 50 iterations or stagnation of 10, whichever comes first. So our solution space is affected because we have three things. We can't graph it in a 2D space. It's basically a cube, but we have, again, the QI, the D, and the B. Here's a synthetic time series to show how this is going to work. In the time series, the QI rate was set at 1,000 barrels, and time is expressed in months. The decline rate is 5%, 0.05, with a B factor of 0.8, and we added 50 units of random noise just to make it a little bit more realistic. And when we fit this function, and again, the only thing that changed with the algorithm itself is the fitness function and those and to initialize the swarm. So when we apply the PSO, we're going to wind up with a trend that looks like this for a minimized error of 41.5. And what we are interested in is this projection of the curve out into the future so we can determine what that forecast is going to look like. We have three values that we're solving for, so we can't just show them all on one chart. Instead, we broke it out with decline being the common denominator on the x. B is for the chart on the left, QI, chart on the right. And we're showing the migration of basically the global best through time. In this case, it's actually the root mean squared error. We're trying to reduce that. So you see sort of how it drifted down and the new configurations for B and DI, Q and DI as such. Now, instead of the global best, we're looking at the swarm cloud in dB and dBQI space, colored by iteration, showing the cluster concentration and movement. So you can see where we started with the blues, with the greens of the iteration, and then moving towards the reds at the higher end, and where again the particles are starting to converge at those optimum locations. The algorithm in this situation moves rather quickly, so it doesn't take long at all if you were to apply this algorithm through hundreds, if not 1,000 wells on a regular basis. That could be solved in a matter of minutes. Here we are looking at the swarm, and we're coloring by root mean squared error, showing the bullseye of final determination. And I just put this one in here to show you how the societal component causes those particles to converge towards the final determination. Use case number 4, landing the LEM on the moon. So before there was Tetris, before Pong, there was the lunar lander game. And Pong came out in 1972, Atari's first and the first big commercial success as an arcade video game. Tetris came out in 1984. Technically, the video game of the lunar lander came out after Pong, but the lunar lander text-based simulation came shortly after the Apollo 11 moon landing in 1969. So the goal here is to provide the right amount of thrust for each time interval to achieve a soft landing. We can think about having time series of 30 steps. So each one of those steps is going to be a dimension we're going to solve for in the solution space. And for each one of them, we want to determine a thrust amount that can range between 0, free fall, or some thrust amount to reduce the speed at which the LEM is going to hit the surface of the moon. And that picture there is of a teletype machine. Look, the monitor doesn't exist. This is what I used back in, middle school decades ago to interact with this particular game. That's how old this thing was. The trajectory of the LEM approach on the moon is going to be based on classical physics. We have some inputs here. So the little a is going to be acceleration, big A is deceleration of thrust. G is the lunar gravitational constant, which is going to be 1.6 meters squared. V velocity, H height above lunar surface, F remaining fuel, and T is time. So those equations are the current velocity is the initial velocity plus the acceleration times delta T. And let's say that delta T is going to be a time step of 10 seconds. A is negative G during free fall, and A is equal to A minus G during thrust event, time step with thrust event. H is dependent on the height initial of the time step plus V initial delta T plus acceleration delta T squared divided by 2. And we're calculating our remaining fuel as such, and also moving the time step up through the sequence, so that with this 30 intervals of thrust applied, we can determine at each time interval the velocity, the height at which the LEM is traveling, and where we're going to touch the lunar surface and at what time. Here are the rules of the game. The objective is to land the LEM, have a velocity at time of surface impact of greater than -5 meters per second squared for a successful landing. I say negative here because we can think about when we're decreasing our height, we are going down. And so the velocity is going to be negative. If we're moving away from the moon, the velocity is going to be positive. In this case, we want a velocity of greater than -5 meters per second squared at time of landing. Given starting height of 10,000, starting velocity 0 meters per second, time limit 300 seconds. That translates to 10-second intervals and 30 time steps. Starting fuel, 55 units. Fuel consumption per time interval, there's a limit here of 8 units. So we can range anywhere between 0 and 8. And the deceleration per fuel unit burned is going to be 0.5 meters per second squared for a maximum of 4. Rules of the game. Motion is in the vertical direction only to keep things simple. There's no downfield motion, as it were. No thrust available after fuel exhausted, even if the PSO calls for it. And no thrust after touchdown. Essentially, at touchdown, the engine shuts off. Touchdown may occur mid-time step. PSO parameters, number of particles is 100. And as you can imagine, the more complicated the solution, that usually ties with how many variables you're trying to solve for, the more particles you're going to need. So in this case, I used 100. C1 and C2 set to 1.5 and the inertia coefficient set to 0.9. The PSO position vector then, again, the things we're trying to solve for, is going to be thrust rate per time interval of 30 elements. With 30 time steps, there's lots of opportunity to get it wrong. Threading the needle on a profile can get it right, but PSO has no default strategy or heuristic per se other than to attempt to optimize the objective of minimizing the impact velocity. The human might try these strategies at various degrees of success. However, if you fire the rockets too soon and the LEM moves away from the moon, fuel then runs out and free fall happens, making a huge crater. Fire the rockets too late and thrust cannot reduce the impact velocity in time for a safe landing. If the thrust rate is too low, LEM will hover as time and fuel run out and then free fall and crash. A strategy where you allow the velocity to increase early on and then start tapping the brakes later towards the end for a sigmoidal height versus time profile would be an optimum way to go. Let's see some PSO results here. So on the right is thrust profile and touchdown velocity per iteration. So with the initial swarm, we can see we had a touchdown velocity of negative 80 plus. I mean, that's going to be very, very high. But the algorithm gradually improves through the iterations and finally has successful stopping conditions at iteration 12. If we take those iterations then and look at the individual time steps, how much thrust is applied, this is what you get. And what I found interesting is that strategy to produce that sigmoidal curve is kind of what the PSO is doing. Through the iterations, it starts to minimize the thrust that's used in the early time steps and apply them towards the end time steps. Notice we quickly did not apply the thrust in the later time steps because we ran out of fuel, essentially. So what we want to do is have, again, that idea of keeping the thrust off towards the early part, hitting the thrust hard at the end. As a matter of fact, our second and third last time step of thrust, we used the maximum amount, and then we achieved a thrust of 5 before we touch ground at a very, very small velocity, less than negative or greater than -5 for a successful landing. Here are the results through time. You can see the deceleration by the thrust applied. Those are the orange bars. And then that nice sigmoidal relationship of height versus time is the blue. The velocity shows how we're increasing, we're actually more negative velocity in the early stages as we're increasing our fall towards the moon. But then as we hit the brakes with the thrust, it starts to come back up after iteration 10. And our remaining fuel, we end up using all our fuel for a successful landing of -0.77 meters per second at a time of 170 seconds. So a nice job by the algorithm to find that optimum landing or thrust time series. The last use case I want to show you is called the pooling problem, and that is to decide which and how much product to blend at what recipe. Let's first consider the conventional situation of dedicated tank blending, where I have A, B, and C in their own tank to produce two products of different properties. This is the classic product mix situation that an LP or linear program can solve quite quickly. If, on the other hand, two of my raw materials must go into a single tank, tank P standing for pool, that mixture of how much A and how much B to use is now subject to optimization to maximize the profit from selling those two products. And because of that, it can no longer be solved with linear programming. Instead, you would use techniques called sequential linear or nonlinear programming. Now let's see if PSO can also provide an acceptable answer here. And I've adopted a problem posed originally by a person named C.A. Haverly back in 1978. And we have those A, B, and C. You can see the costs involved and then the sulfur. A is high sulfur, B is very low sulfur, C is in the middle, and then those costs are attributed to how much sulfur, sulfur being something that you want to minimize. On the product side, I have product X, a value of $9 per unit. For relatively high sulfur, up to 2.5% sulfur, I can sell up to 100 units of that, and product Y is low sulfur at $15 per unit, and I can sell up to a maximum of 200 units there. Here is a node diagram of what this problem is going to look like. So we have our raw materials, A, B, and C nodes, our products X and Y, that intermediate pool of a mixture of A and B, and then the arcs that connect them, which is simply the name of the two nodes that they tie to. The movement of the materials from left to right, and these are the equations then that we can use to determine the amount that we're going to use of these individual raw materials to blend up our products in an optimum fashion. The first one that we're going to use is overall mass balance. As you can see, all the raw material quantities have to equal all the outbound product sales. This is the pool in terms of its inflows. This is C in terms of the other constituents. So C must balance with the sale of materials minus the mixture of A and B. Here is the edge balance of a pool. So you can see that the vectors in have to equal the vectors out. We have edges coming from C, as you can see here, edges coming from X, edges coming from Y, and then also, what are those values in terms of sulfur? So we have sulfur in the pool, as you can see here, where that little S, AS, and BS are the sulfur concentrations of those raw materials. Sulfur in X is shown here. That's our sales product. And then finally, sulfur in Y is shown here. Let's parameterize this problem. So we're going to have a little x equal to the percent of the maximum x demand. Same goes for the y percent. We have little xp equal to the percent of x filled from pool. Same for y. We have little pa, percent of pool filled from A. Same goes for b. And now we're talking about quantity. So we have p, the quantity of the pool. These are all capitals now. And xc, the quantity of C in X, the quantity of C in Y. Now we have A in P, B in P, and xp is a quantity of X coming from P, and yp, the quantity of Y coming from P. But since we know X fill is equal to that percent of the X demand times the X demand, same goes for Y. Quantity of X coming from P is the same as X fill times the percent XP. Same goes for YP. We have the percent of PB equal to 1 minus PA, and the quantity of A and P is equal to XP plus YP times that percent of P coming from A. Conversely, this is the one for PB, since we know the relationship of PB to PA. The pool itself is made up of A and B, And X, the amount coming from C, is X fill minus the quantity of X coming from the pool. And YC is the same thing. So knowing that, and we work that back into our parameters, this now collapses to these 5 variables that we want the PSO to solve for. So the PSO position vector is going to be this as such. All variables range in the value between 0 and 1. All quantities and sulfur concentrations may now be computed. The objective is to maximize profit, which is going to be the amount of revenue minus the cost. So we have the revenue coming from our product demand times the fill rate minus all these costs associated here. So to preserve continuity in PSO, let high sulfur product be price penalized instead of quantity limited. So PSO doesn't really deal well with constraints. It assumes that the solution space is continuous between the bounds. But we can simulate that by giving a discounted value if our computed sulfur is above the limit. It may also be a benefit in situations where you want to negotiate with the customer and perhaps say, hey, what would you expect as a discount if I were to sell you something instead of being 1.5% sulfur, it's 1.6. How much is that worth to you? And you might find out that that's worth more to him than it is to you, in which case it might be advantageous to do that. And PSO lets you solve for that by trying to manipulate those discounts. Okay, let's look now at the optimum blending situation that PSO solved for. So here is our answer that we came up with. It may seem counterintuitive, but we didn't actually fill any of the X demand. That fill was equal to 0. We did fill all of the Y, 200 units at a sulfur of 1.5%. And the pool was composed completely of raw material B. And we used C to end up balancing the amount of B at 1%, and then we could balance that with C to come up with the 1.5, a little cheaper than if we just used B exclusively. But that's what we came up with, and it may seem counterintuitive that we didn't fill all of the demand that was available. So here's sort of what that looks like. We have the profit, revenue of $15 times 200 units, minus the cost of A, 0 was used, minus the cost of B, minus the cost of C, for a total profit of 400. So what we ended up doing was selling only Y and don't use any A. Okay, let's see what that looks like through the iterations now. So in the first graph here, the top one, we have our percent fill of X and Y. As you can see, the PSO, it actually started with filling X, but then it must have found a new global best and decided to start filling Y, as you can see here around iteration 3 or so. The dashed line is the profit, and then we have 3 other variables we're looking for. The percent of P in X and the percent of P in Y. And so that is shown here, the percent P in Y. As you can see, we started out very low and it jumped up, and finally it came down to about 50% as the remainder to fill Y is coming from C. And this is how we wound up with the profit of 400. And you could also see how the percent of A used in P came down to 0 around iteration 14 or so. And that's where it stayed until we achieved stagnation, which indeed, that 400 does happen to be the optimum answer for this problem. Let's say you don't trust that answer and you still can't believe that in that original problem we didn't fill any of X. So let's add a blending constraint where we say X fill has to equal 100% of X demand. This constraint is easy to set up by adjusting the boundaries of the impacted variable X. So let's see what happens. In this particular situation, we're still not going to use any of A. We're going to use 100 units of B and now 200 units of C. What's going on here is that all of X is filled with C, and so the sulfur percentage of X is now 2%. We filled 100 units. Y is the same. It's coming from the pool and is coming from C. But when we do the math here, we wind up with a profit of only $300. So what happened is we ended up selling more, we had a sulfur giveaway, and we profited less. Let's say now you still can't believe that we're not using our cheapest raw material A, and so you come up with a constraint that says the percent of A and P has to be greater or equal to 25%, and X fill has to be greater than or equal to 50% of X. So this again we can set up quite easily with adjusting our bounds. But what we wind up with is a situation such as this. Yes, we did use 50 units of A going into P, and to make up the balance, we used 150 units of B for a sulfur concentration in the pool of 1.5%. We filled 50 units of X and 200 units of Y, which is coming from, Y is coming solely from our pool, and X is coming from C. So this situation, we did sell more material, we did sell more units of material, but there was a sulfur giveaway on X, and we ended up profiting less, only $250 now. All right, we looked at those 5 use cases. Now let's put together some guidelines to see if your problem is going to be suitable to be solved with PSO. Let's look at problem characteristics. Is it nonlinear or a complex objective? Is it difficult or impossible to solve mathematically, such as with linear programming or nonlinear programming or sequential and so forth? Is gradient information unavailable or unreliable? Are the variables continuous? And does the problem in theory align with the swarm metaphor? If we're not talking about searching an objective space, but we're rather trying to sequence events, that might be a different type of meta-heuristic that we want to use. Let's look at computational fit. Can we compute the fitness at all points in the solution space? Do we have tolerance for stochastic outcomes, such as I mentioned that because we're using some randomness, each time we solve, those random numbers may be changed that are used in those computations. So we have to account for that we do have stochastic outcomes and we won't always get necessarily the same answer each time that we run it. Is the evaluation time within your budget in terms of how much longer, how long are you going to wait for an answer? That trade-off of accuracy versus time to solve. Moving on to dimensionality and constraints. Moderate dimensionality. So once you get past 100 variables, it really tends to slow down, and you may need to use some other heuristics to manage those, or again, see if you can solve it mathematically. Does the dimensionality, so the number of variables, remain static through the search execution? So our problem all of a sudden didn't change as we got into a certain solution space from more or fewer variables than we started out with. Can constraints, if they are such, if you do have them, can they be managed through penalty functions? And importantly, is the search space bounded? So do all variables have an upper and a lower bound? We have desired outcomes too to look at. So we want to avoid local suboptimality. So that's what PSO is good for. It can also be used for multi-objective trade-offs. I didn't get into that. It's kind of beyond the scope of this, but maybe I'll show that in a future presentation. and we can use flexible and multiple stopping criteria. These are the steps involved to implement PSO for your problem. First off, let's verify with that checklist I just gave you the problem suitability. Next, we want to define the problem. So determine the objective. What is it that we're trying to do? Minimize delivery costs, maximize returns, etc. Identify the variables that are necessary. Write an objective function with those variables. Then the algorithm setup. Develop an initialization function. Set hyperparameters, the C1, the C2, and so forth. Identify stopping conditions. Use a PSO library if available for your programming language. I know that in R and Python, these libraries exist, and this may be a simple way to get something going. However, as I said, the algorithm is so simple that you can easily set this up yourself as well. But yeah, give those libraries a try if they are available. Moving on to testing and evaluation. Test on historical or simulated information if you don't have historical. Decide on the desired accuracy and speed. Oftentimes, I don't need the ultimate best answer. I need something close. And as you saw in those iterations that I used for doing the radio tower search, after we got past like iteration 50 or so, it really took many more iterations to significantly improve the coverage. So determining when to stop is good, and sometimes you don't want to go to the ultimate end just to get a slightly better answer. When evaluating hyperparameters, consider using a constant random sequence. So that would be in the testing. That way I can avoid that the answer just changed because of the random number sequence that I use, but I'm really looking at evaluating a C2, for example, of a value of 1.0 versus a C2 of 1.5. Use the same random number sequence. Validate and or adjust the objective function as necessary. Oftentimes when you get into this thing, you realize that, oh, I need to tweak that objective a little bit. It wasn't quite right how I formulated the original problem. And there are other, because the algorithm is relatively simple, it's easy to add these little extra things such as particle extinction may be necessary or maybe desirable if you want to preserve the swarm diversity, for example. Finally, there's deployment. Develop business-centric result reports that communicate the findings and talk in the language of the business rather than the language of particle swarm or C1 or C2 or whatever, Deploy it in your business environment, whatever that may be. It may be on your laptop, it may be on a network, it may be in the cloud. Your IT professionals can help you with that. And finally, monitor the performance and refine as needed. Oftentimes, if your problem is successful and you're giving good answers to a certain business opportunity, they start coming back with more questions. Oh, can it do this? Oh, wouldn't it be cool if we could expand it to take on this other functionality and so forth? So that's when you know you've hit success, and when you go through different iterations of actually making the problem that you're trying to solve more refined and improved. If you made it this far, please like, share, and comment. Thanks for your attention. I'm sorry it went over 1 hour. I'll try to keep it a little shorter next time. Hope you found this useful and encourages you to try PSO for your next optimization problem. I'll see you next time.